Question number 5 is about a street light. And this is a classic related rates problem. And I love street lights, so I think they're just so romantic. I do. And I love doing problems with them. So here's a 15-foot tall pole. And it says a 6-foot tall man is walking away from the pole. So let's draw him in. He'll be about here, with a speed of 5 feet per second. So I'll just write that over here to remind us that we know that. It says, how fast is the tip of his shadow moving when he's 40 feet from the pole? So we know this distance is 40. And we know that the shadow's here, of course. I'll draw in his little shadow. The man is walking. He's a stick figure, but he's also directly orthogonal to us, so he just looks like a straight up line on the triangle, doesn't he? One thing we may want to abuse about this is that if you remember from geometry, this triangle, if he has a triangle inside him like this, they're going to be similar triangles, which means the ratio of this side and this side is also going to match the ratio of this side and this side. We'll use that in a minute, I'm sure of that. I want to give these a label. I'm going to call this x, this distance. And I'm going to call the shadow distance s for shadow, because why not? My s's always look like 5s. I hate that part. That's close enough to be an s. Okay, good. So what can we do from here? Well, let's look at what they want first, and maybe we can work backward from there. How fast is the tip of his shadow moving? So that's a dt. That's a time thing. And I think that we want to focus on that, right? So let's say the total length here, of course, is x plus s. And if I take the derivative with respect to time, I can separate these because they're simple addition. So I'll call it dx dt and ds dt. Because we're trying to find out how fast it's moving from here, right? And that's x plus s distance. That's why we're taking the derivative this way. But we can add the derivatives up separately to get the answer, and that's really cool. So we need to find a relationship between x and s. I'm so sorry about that noise. Now, we know that because they're similar triangles, I can say 15 over x plus s. And I can also say 6 over s, since they're similar triangles. And if I multiply them up like this, then I'm going to get 15s equals 6x plus 6s. Subtract the s's away and you get the 9s, of course. So I'm going to find that s equals 2/3 of x. Pretty sure that's true. Now, we're getting warm because we can take the derivative with respect to time. And what are we going to get? ds dt equals 2/3 dx dt. Nothing crazy. And some of this we're told because they told us he's walking away at 5 feet per second, which is this x value is increasing. So that's our dx dt right there. So that would make it 10/3 because I'm timesing by 5 for dx dt. And we already know dx dt is 5. I'll write it here if you want. Which means I kind of already have my answer because I get 5 plus 10/3. And I can make this 15/3 so they match, and then we can just add the like terms together and we get 25/3. So that's going to be like 8.333 feet per second. And that's the actual answer. So the thing to notice here is that first we have a triangle whose length is x plus s. Separate them into the two parts, plug in the one that we got, but then find the ratio here. Find where ds dt factors into this. And you're there.